Well, hello everybody, and welcome to lecture 4 of our Calculus 1 class. So today, we're going to talk about linear approximation, and you may have noticed by now that I oftentimes feel like, okay, now we're really getting to this is the core concept of calculus. And every time I say that, I mean, I'm not lying. I mean, it's kind of true, but also if you pay attention, if you notice, if you think about it, a lot of times these concepts are coming back. The same central concept is coming back in several different guises. And what we're going to talk about today is really a reformulation or a reinterpretation of things that we've been talking about all along. But I would again say that this is like very core to the calculus, and in particular the differential calculus. So, there's differential calculus and the integral calculus. There's the two main branches of calculus. The differential calculus is really all about the tangent line and rates of change and some other things that we're going to talk about tomorrow. But this week, we're really going to be striking at the core of this, I would say, more so than even we have before. But using this concept of the tangent line repackaged as something called linear approximation. And linear approximation, it can sometimes it can come across as sort of like, oh, this is an application of calculus, or this is a fun thing you can do with calculus. But it's more than just a fun thing you can do with calculus or an application of calculus. It's both practically important and theoretically important. And its practical importance can seem a little bit underwhelming at first when you first see it, and it will be improved upon by what we talk about tomorrow, but its theoretical importance is also significant, as can be seen with the chain rule that we will prove after we talk a little bit about. First, we'll talk about the essence of linear approximation, then we'll talk about some applications of linear approximation, and then we will talk about the chain rule, which is the first theoretical application of linear approximation that we'll run into. Now, in the mathematical world in general, there are countless theoretical applications of it, including my research. I take linear approximations. And they're very important and for lots of people's research who are at this school and elsewhere. But anyway, so let's go ahead and do it with linear approximation. So the idea with linear approximation is really, computationally it's going to be very familiar, but in terms of how we interpret it, it's going to be sort of new. So we have a curve, y equals f of x, and we have the tangent line to the curve, y minus f at the point, let's say this is the point x0 for the x coordinate, and the y coordinate is f of x 0. So the formula for the tangent line is going to be y minus f of x 0 equals f prime of x 0 times x minus x 0. So this, I've said in the past that this is my favorite way of writing the tangent line. But that might not be completely true. I kind of prefer actually y equals f of x0 plus f prime of x0 times x minus x0. Which, if you notice, I mean, it's obviously equivalent. We've just added f of x0 to both sides. So this is sort of like the slope-intercept form, only with the horizontal shift of x minus x0. And so the idea with linear approximation is that the tangent line is approximately equal to the function. So if x is close enough to x0, then the tangent line is approximately equal to the function. And the closer it gets, in fact, the better of an approximation it is. And we can express this as saying saying, I'm going to write it over here on the other side, that if x is close to x0, then f of x is approximately equal to f of x0 plus f prime of x0 times x minus x0. So, to say that x is close to x0, this is the same as saying x minus x0 is small. So the difference between x and x0 is small. So, so all this statement says, this is, and these mean approximately, if you've never seen that before, this curvy sort of equal sign looking thing means approximately equal to. And what this is just a mathematical statement of the fact that the tangent line is close to the graph of the function. So an immediate question that you might be having is, well, this seems awful convoluted, why would we do this? I mean, we know f of x, why would we prefer this bizarre looking, well, not necessarily bizarre, but this complicated expression that takes multiple steps to get? Why would we prefer this expression over this expression? And that would be a reasonable response to functions like f of x equals x squared, f of x equals x cubed, and the types of functions that you can explicitly compute. I give you an x value, you can explicitly compute it. But say we know some values of f of x0, and we know some values of f prime of x0, but we don't necessarily have an explicit, and we don't necessarily have, off the top of our head, or on a desert island, we don't have an explicit formula for f of x. So say like f of x equals the square root of x. If f of x equals the square root of x, then there will be some special values for which we do know the answer perfectly without our calculators. Like a square root of 64, f of 64 equals 8. Right? But if it was f of 65, we can't say what it is without typing into our calculator, or using the methods of calculus, like we're about to do, we can approximate it. So, okay, so square root 65, which equals, say, f of 65, where f of x equals square root of x. So this is, by linear approximation, approximately equal to f of 64 plus f prime of 64 times 65 minus 64. And we know from the test, on the test, I think it was problem 4, that f prime of x equals 1 over twice the square root of x, right? And so this is going to be, square root of 64 is 8, and this is going to be f prime of 64 is 1 over twice the square root of 8, so 1/16, and then times 65 minus 64 is just 1. And then in decimal notation, this is 8.0625. So I invite you, no, I implore you to put square root of 65 into your calculator and see how close it is to 8.0625. Now, these may not be the first 4 digits, they may be something near to this, but it should be pretty close. Now, what does your calculator do, or how would we get closer to this? Actually, I don't know exactly what your calculator does. It probably does some high efficiency tricks. But how would we approximate this arbitrarily well to make it as close as we could possibly want it to be to the exact answer? Well, that's something that we'll get into more tomorrow. But here's a first approximation with the tangent line. And let me draw a quick picture of what we just did right there. So, say we have f of x equals the square root of x, and I'm gonna draw a different zoom. So if f of x equals square root of x, say we have here x equals 8, or sorry, x equals 64, and square root of 64, y equals 8. So what we've done is we've evaluated 65. This point on the tangent line is 65 and 8.0625. 8.0625. It's this point right here. And that's approximately the same as what's on the graph. So that's what we've just done, interpreted visually. And other applications of linear approximation are in the laws of nature. Models refer to the laws of nature. Sometimes it's intractable to try to formulate the laws of nature in the most precise form that you can possibly get them into. So you want to linear approximate these laws. And so, for example, the mathematical formulas modeling the propagation of sound waves that are generally used are use a linear approximation to get that model. And what happens is when the tangent line gets too far away from the curve in the approximate formulation of the law, or more accurately, it would be a problem when the actual curve bends down, that you could have a problem where the linear approximation entirely ceases to be valid or helpful at all. And an example of that is the speed of sound and the breaking of the sound barrier. It's when the linear approximation model of sound waves ceases to be valid. Because if you look at the most, if any of you go on in math, you'll eventually see this. If you look at the most, or go on in math or physics, if you look at the most, the linear approximation model for sound waves that works for sound waves up to the sound barrier, or before the sound barrier, that there's nothing inherent in those equations that tell you that there's a speed of sound or that you're going to break the sound barrier. So that's because they are only a linear approximation and they're valid up to that point where the sound barrier is broken, which is where x ceases to be close to x0. Now, how close x is to x0 will determine how good the approximation is. And if you were paying attention to the last example, you could say, well, so x equals 65, x0 equals 64, x minus x0 equals 1. So x minus x0 equals 1, that's an okay approximation. It's not, the approximation is pretty good. That's kind of small, but it's not that small. I mean, this 1 is fairly large, and depending on the context, 1 could be fairly large or fairly small. So there is some quality control that comes into play with how small x minus x0 is, and the approximation might cease to be very good for x minus x0 too big. So tomorrow we'll talk about more precise approximations, but this is a valid concern that, okay, so it worked last time when we did it with square root, but is it going to work in general? And the point is that you have to check on these approximations. You can't just do a linear approximation with arbitrary x minus x0 and say, call it a day, like I have a good approximation. The approximation might not be good. So that's just a fact of life with approximations is, well, sometimes you actually can tell how good they are. And with linear approximation, there are ways to tell how good the approximation will be in advance, so you know how far you're going to err when you do this approximation, but we're not really going to get into that in this class. But we will talk about ways to get better approximations soon, as in tomorrow. But okay, so there's some practical applications of linear approximation, of which there are countless more. We've only touched on one practical mathematical one, and one in very vague terms I've spoken of a physical application. But let's consider a theoretical mathematical application, which is going to give us a new differentiation rule, probably the most important differentiation rule that many of you may have already heard of, called the chain rule. So recall that our linear approximation was f of x is approximately equal to f of x0 plus f prime of x0 times x minus x0. So chain rule, just a quick reminder of that. So chain rule is we want to find the derivative of f of g of x. So f of g of x prime, which, we'll also write this f of g of x, write it as just a new function, f of g, and this is it's somewhere between an O and a dot, and it means of, so this reads f of g of x. It looks like fog, but it's not fog, it's f of g of x. And it's not a multiplication dot either. It's this little thing that's somewhere between a dot and an O, and it means of. It denotes function composition, so f of g of x, derivative of this, is what we're seeking. This is what we seek. So, well, let's do a linear approximation near x is 0. So, f of x is approximately equal, we're looking for f of g of x. F of g of x is approximately equal to f of g of x0 plus f prime of g of x0 times g of x minus g of x0. Now, some of you might be fully comfortable with what I just said, and many of you might feel like, wait, haven't you just skipped a step? I guess I sort of have skipped a step, because what I'm really doing here can be made more, you can throw in another step of saying w equals g of x, w0 equals g of x0, g of x0. And then this statement up here is the statement that f of w is approximately equal to f of w0 plus f prime of w0 times w minus w0, which is a straightforward expression of linear approximation. It's the same thing, only with x replaced with w. Of course, variables can be named whatever you want, but then remember that this substitution, we can work that back to this. Okay, so now I'm going to erase this expression because it's just an intermediate step. But so this is a good start, but we can further approximate it by approximating g of x minus g of x0. So this right here, this is approximately equal to g prime of x0 times x minus x0, right? I mean, that's just the formula for the tangent line would be y minus g of x0 approximately equal to this, or is equal for the tangent line, so that means g of x in place of the y in the tangent line, so g of x is minus g of x0 is approximately equal to g prime of x0 times x minus x0. So then using that I'll leave that up. So using that approximation, now this whole thing this whole expression now can be seen to be approximately equal to f of g x0 plus f prime of g of x0 times g prime of x0 times x minus x0, where we've here done, it's called successive approximations. First we approximated f of g of x minus f of g of x0, and now we're going to approximate in terms of g of x and g of x0, and now we've approximated g of x minus g of x0 in terms of x and x0. So you could, and I would be perfectly satisfied saying, well, this is the slope of the line in the linear approximation, the slope of the tangent line. therefore call it a day. This is the derivative. But if you're not satisfied with that, we could take another step to prove this. Of course, one way or the other, I guess it's not fully rigorous. I'm using terms like approximate and not doing all the epsilons and deltas, as they call it. But regardless, we could take another step in proving this, and we could say that all of this shows that, so we have f of x is approximately equal to f of x0 plus f prime, sorry, skipping something here, f of g of x is approximately equal to f of g of x0 times, plus f prime evaluated of g of x0 times g prime x0 times x minus x0. And what we can do is we can subtract this from both sides. So we have f of g of x minus f of g of x0 is approximately equal to f prime g of x0 f, I'm going to write it, sorry, just a little bit further over, f of g of x minus f of g of x0 is approximately equal to f prime g of x0 times g prime of x0 times x minus x0. And then we could divide both sides by x minus x0. And then we could set x minus, sorry, let me turn off this. We could set x minus x0 equal to h. And then we could rewrite this as f of g of x0 plus h, right? Because if x minus x0 equals h, then x equals x0 plus h minus f of g of x0 over h, that this is approximately equal to f prime of g of x0 times g prime of x0. And then if you take the limit as h approaches 0, this is going to be the derivative of f of g of x, right, by definition. But then this side doesn't involve h, so this is the exact value of that limit. And so that gives us the chain rule. And so the chain rule is that this derivative here, so we see now we found this equals f prime of g of x times g prime of x. And what exactly do we mean by f prime of g of x? We mean that the function f is evaluated at g of x. That f prime is evaluated at g of x, and then we multiply it times g prime evaluated at x. So maybe an illustration of this will help. So how about we consider sine of x squared prime. So this equals f of g of x, where f of x, or sorry, where f of w equals sine of w, and g x equals x squared. So, sorry, there should be a prime right there. So this now equals f prime of g of x. So f prime is cosine of w. So cosine of g of x is this first term. This first term is this term is cosine of g of x, and the second term is g prime of x, which of course g of x is x squared. So this is going to be cosine x squared times 2x. And of course, you might want to move the 2 to the front. It looks a little less awkward. Yeah, in fact, you might want to move the x to the front too. I mean, it doesn't really matter. Whatever you write on the test should be fine. But just compulsively, I feel like moving it around like this. But so the point is that it helps to think in terms of this so that we're entirely clear on what it means to say f prime of g of x. Because of course, f prime of g of x is not the same as f of g of x prime, right? Because this now is a function. In this case, it's the function, I didn't write it here, but in this case, it's the function, so f prime of w equals cosine of w. So it's f prime is a function which is then evaluated at g of x. So that's an important thing to keep in mind. We'll touch back on that in a little bit. But before that, let's consider some more examples. So one good example is a simple example, cosine of x to the n. The derivative of this equals the derivative of the function w to the n, right? Because this is w to the n, you could say. And we first take the derivative of this function. So n times cosine of x, this is our w, raised to the n minus 1 power. And then we multiply it times the derivative of cosine of x. So that's going to be negative sine of x. So all in all, the answer is going to be n times cosine of x to the n minus 1, which, again, this is the notation that's usually used for ordered reasons. So n times cosine to the n minus, we have a minus sign here, n times cosine to the n minus 1 x, all times sine of x. So there's one example. Another classical example that is very helpful and useful to think about is and actually will have theoretical import that we will soon see, but e to the g of x, the derivative of this function is g prime of x times, first I'll say it's the derivative of e to the w evaluated at g of x, which is just going to be e to the w again, right? Which is just e to the g of x, and then multiplied times g prime of x. So, for example, e to the cosine x, the derivative of e to the cosine x is going to be e to the cosine x times derivative of cosine x, which is negative sine of x. So, yes, this holds for any derivative that we put in the exponent for e to the x. So, okay, so let's go on and do one more example before we move on to another theoretical fact. So, one more concrete example is 2 to the x. So if you really have reviewed the log rules and are comfortable with them, this what I'm about to say will make perfect sense. If you haven't, now is probably a good time to do so. So this equals e to the natural log of 2 times x. And so then the chain rule says that the derivative of this equals the derivative of this. And then on the inside of this, we have a linear function. So the derivative of the inside function is just going to be the slope of that linear function. So, and that's the terminology that's often used is when you have f of g of x and you're taking the derivative, you would say derivative of the outside, which would be f prime of g of x, times the derivative of the inside, which would be g prime of x. But anyway, so this would be ln 2 times e to the ln 2 times x. But then this expression is just 2 to the x, so this is ln 2 times 2 to the x, which agrees with the calculation that we had for this before. So of course that's good. If it didn't agree, that would be thoroughly disturbing, but of course math is all consistent, it's all true in all possible worlds, so nothing to worry about. It'll always, if we proceed correctly, we'll always try to answer the same question. We should always get the same answer. So let's use the chain rule to find the derivative of the natural log function. So this is sort of interesting. We have, let's first say, so the derivative of just x is 1. So 1 is just the plain old derivative of x. Then we can rewrite x as e to the natural log of x. So the derivative of e to the natural log x, and then using the aforestated result with what happens when we apply the chain rule to e to the g of x, is we get g prime of x, in this case ln prime of x, multiplied times e to the ln x. This, of course, this e to the ln x is just x. So this is going to be x times ln of x. Ln prime of x, derivative of ln of x. And this shows, by dividing both sides of the equation by x, this shows that 1 over x equals the derivative of ln of x, or we could write it the other way around, ln prime x equals 1 over x, which is quite interesting. And this actually, you could also write x to the minus 1. And so this is sort of a gap in the power rule, because the derivative of x to the 0 is just 0, which has nothing to do with x to the minus 1. But the derivative of ln of x is x to the minus 1, which is I think is pretty interesting. So so now let's consider the power rule again, revisit the power rule, and now we'll have the power rule for the most general case. So x to the r prime, where r is any real number, so let's say r, any real number not equal to 0, so r not equal to 0, x to the r prime, we can rewrite x as e to the ln of x times, and so this becomes e to the ln x to the r prime. But let's go ahead and use log rules to move the r inside of the exponent, and then using the chain rule, we get r times ln prime, because r here is a constant, so there's no derivatives being taken of a constant, but the derivative of this function is going to be r times ln prime of x times e to the r ln x. But this expression, as we said before, this is just x to the r. And this is just 1 over x. So we get r times 1 over x times x to the r. And then this equals r times x to the r minus 1. And so now we have the power rule for arbitrary real values. So there it is. This works for fractional powers, works for irrational powers. Yeah. But it doesn't... Okay, I can sort of... Yeah, it works as long as r is not equal to 0. It doesn't work for 0. Instead we have, as I mentioned before, we have this gap, which is filled in by the natural log in the case of 0. So earlier, you'll notice that I did something that may have been surprising, which is I had an equation and I just differentiated both sides of the equation. In particular, when I had x equals e to the ln x, and then I differentiated both sides of the equation. Now, of course, it turns out you can actually do this in general, and this gives us all sorts of wonderful methods for taking derivatives of things. So let's consider the inverse tangent function. So, and what this does is this relates slopes to angles, right? Because if you have a given angle, a given angle, it can be any angle, then theta, then tangent of theta equals sine theta over cosine theta, which is going to be the slope of this line. So if we can find the inverse of tangent, the theta for which corresponding to a given slope, then, so let's say this slope is m, so tangent theta equals m, so it's called arctangent of m equals theta. So if we could find this, then we would have fully understood the relationship between the angle and the slope. And as I mentioned before, this is what Madhava had found long before the rest of calculus was elaborated, as far as we know. And we're now in a position to do it, granted by a much different way than Madhava did it. But we're in a position to determine at least the derivative of this arctangent function. Then tomorrow we'll get to how to approximate it really, really, really well. So tangent, so this is a very similar idea to what we did before. So tangent of arctangent of m equals theta. So this is, arctangent is the inverse tangent function. It's sometimes written as tangent inverse of m. But, regardless, it's the same thing. I kind of like arctangent, but of course, tangent inverse is sort of more standard. But either way, so this equals theta. What am I saying? This equals m. This equals m. The tangent, because this right here, this is our theta. So tangent of theta equals m. Tangent of arctangent of m equals m. This is, an inverse function. That's the way that inverse functions work. So let's take the derivative of both sides with respect to m. So this side becomes 1, and then this side becomes secant squared of theta, which is arctangent of m, times the derivative of arctangent is, derivative of the outside times the derivative of the inside. This is the derivative of the, I forgot the c in secant. The outside, this is the derivative of the inside. So then we can rearrange, we can use some identities and rearrange. So recall that secant squared of theta equals 1 plus tangent squared of theta. So this whole thing here can be rewritten as using this identity. You can rewrite this as 1 plus the square of the tangent of arctangent of m, but tangent squared of arctangent of m, well, that's just m squared, right? So taking the inverse function, so that's just going to be m squared. 1 plus m squared times arctangent prime of m equals 1. Again, we divide over to the other side, and we get arctangent prime of m equals 1 over 1 plus m squared. Okay, so yeah, so that is our sort of most notable applications of the what's called implicit differentiation, where you take derivatives of both sides. Of course, there are other examples that will be seen on the homework and the recitation worksheets and the test. And actually, in this lecture, we'll get to some more examples of something called related rates, which is coming up soon. But something I'll point out, which will show up on the homework, is that we know from pre-calculus we have several values we get for free for all the trigonometric functions. In fact, how many of them do we have? We have 3 inside of each quadrant, so that's 12 plus 4, 1 for each axis. So we know 16 values. And you can do pretty well with the linear approximations for these inverse functions, or for the forward function. So this gives us a pretty good grounds, pretty good framework for doing linear approximations to trigonometric and inverse trigonometric functions. Anyways, you'll see some of that on the homework and probably on the test. So moving forward to our next topic, which is going to be related rates, which is an application of this idea of implicit differentiation. So sometimes you'll have a function which is defined by an equation, but not necessarily an equation y equals f of x. It could be a different equation. And maybe I'll mention briefly that using this implicit differentiation, we could take derivatives of of arbitrary equations. And okay, I guess I will do this example. I won't follow it through the end because it's kind of an annoying example. I was going to do it, then I decided not to do it. But then I'm thinking it would be helpful just to do it part of the way to illustrate the point. So say y is a function of x, y equals y of x, and then I'm gonna sort of be a little bit loose about the notation as I'm writing it down because things get sort of messy. But it's defined by 2x cubed plus y squared equals 3xy. So then we could differentiate all this stuff and get 3 times 2x squared plus 2y times y prime equals, and then here we'd have to use the product rule. So we would have 3 times, we take the derivative of x and leave y, and then leave x and take the derivative of y, so x, y prime. And all these derivatives are with respect to x, which is why y is a function of x, but x is not a function of x. Well, it is, x doesn't need to be considered as a function of x, so we don't have any x primes in here. The x primes are just 1. And then we could move all the y primes to one side and then divide. So we could have 3, we could rearrange this to 6x x squared minus 3y equals 3x minus 2y times y prime, just by rearranging, and then we can divide both sides by 3x minus 2y. So then we have that this is y prime, and yeah, so this seems sort of like, okay, weird, why are we doing this? But so now we have y prime in terms of x and y, which in general is not incredibly helpful. It doesn't give us everything we need to describe y perfectly, but we can notice that the point x equals 1, and by the way, I highly recommend implicitly graphing this in Desmos, and I'm sending instructions on how to graph implicit functions for Desmos. But so this defines a curve, and the point x equals 1, y equals 1, notice is on this curve because 2 times 1 cubed plus 1 squared equals 3 times 1 times 1. So this point is on the curve, and then if we have a point x close to 1, x close to 1, then we can linearly approximate that y is approximately equal to y0, which is 1, plus the derivative, which we plug in x equals 1, y equals 1 into here. So 6 times 1 minus 3 times 1. So 3 over 3 minus 1, which is just 1. So 3 over 1 times x minus 1. Or, 3x minus 2, as this comes out to be. So that's kind of cool. We can linearly approximate this function without having any clue how y actually explicitly depends on x. We can linearly approximate it near the point 1 and 1. And yeah, I mean, you could plot the tangent line too in your Desmos graph, and that would be very good practice. So I'll write that as as suggested ungraded exercise. Is on Desmos, implicitly graph 2x cubed plus y squared equals 3xy, and also graph the tangent line at 1, 1. Which is given by y equals 3x minus 2. So that's a suggested exercise. And okay, so now let's get into related rates. So related rates is sort of a more story problem type application of implicit differentiation. So let's say that we have fixed point. Say this is the x-axis. This is the x-axis. This is the y-axis. Say we have a fixed point along the y-axis. And let's say that this height here is L0, and as we move along the x-axis, the distance from this point is going to be L. So L is clearly a function of x, right? Because as you move along the x-axis, L is a function of is going to be changing. And in fact, It's the hypotenuse of a triangle here. And so we actually could explicitly write out the dependence of L on X in this example, but it's actually easier to deal with the situation if we don't explicitly write it out, but instead use this implicit differentiation that we've been talking about. So, okay, so how does that work? So the Pythagorean theorem says that L0 squared plus X squared equals L squared, right? This is the one side of the right triangle, this is another side of the right triangle, and this is the hypotenuse. So we can differentiate both sides of this equation, and L0 is constant, so what we get is 2x equals 2, and then chain rule, L times L prime of x. This can be simplified to L prime of x. I'm going to put the x dependence back in. Sometimes for ease of notation, we won't write the dependence explicitly. Like here, no explicit dependence, but I'm going to put the dependence back in. So L prime of x, we divide both sides by 2, then divide both sides by L to get L prime alone. So L prime of x equals x over L, which equals x over, we know from here that L is the square root of x squared plus L0 squared. X squared plus L0 squared. Okay. So that's kind of cool. So that tells us how L is varying in terms of x. So let me write this up in the corner because we're gonna keep working with this. So L prime of x equals now I erased it. Equals x over the square root of L squared plus x squared. So, L0 squared. L0 squared plus x squared. I should write that. So L0 squared plus x squared. Okay, so that's good, but what if we wanted x to be moving over time? So let's say, for example, periodic motion, which would be x is going back and forth along the x-axis, and we want to know what L is over time. So now x is a function of time, so L is going to be a function of time as well. So, okay, so now x, we again have x squared plus L0 squared equals L squared. But now x is a function of t, and so when we perform our implicit differentiation, we're going to need to keep that in mind. So this becomes 2x times x prime equals 2L times L prime. So we again divide both sides by 2L in order to get L prime alone. So we get, this implies that L prime equals x times x prime over L, which is the square, L is still the square root of x squared plus L0 squared. And notice this is not the same expression we have for L prime of x, so this is L prime of t. So this is sort of frustrating. Well, we're saying L prime in both cases, so in one case we're taking the derivative with respect to time, one time we're taking the derivative with respect to the spatial variable x, and we're getting different values. So it seems like maybe some different notation would help, because it seems like these should be the same function. I mean, we've just changed the name of the variable. It's different. But we've really done more than change the name of the variable, because if we'd really been following everything properly, with pure precision, we would have been writing L of x of t, and this right here would then be L prime evaluated at x of t, which is this up here, times x prime of t, which is exactly what this is. Right, this is this expression times x prime. So the notation that's usually used for this is the Leibniz notation, which has infinitesimals implied in it, but we're, of course, not building up this whole class in terms of infinitesimals. But the way that the Leibniz notation works is we would call this right here, instead of just calling it L prime of t, we would call it dl over dt. And then this up here is dl over dx. And then the chain rule, using this notation, the chain rule says in this notation that dl over dt equals dl over dx times dx over dt. So of course, this just looks like fractions, right? If dl and dt were actually quantities, this would just be a simple fraction rule. And indeed, if you interpreted this in terms of infinitesimals, these are fractions and these quantities are infinitesimal quantities, but the way that it probably says it in your textbook is that we mean this purely formally. And if you had a physics textbook, it might take it a little bit more literally and just at some point make a note that they're not being fully rigorous. Or if you were to use one of the fringe textbooks I mentioned before, this would straight up, they would say this is a ratio of infinitesimals. But then, so anyways, the chain rule can be restated in general in these terms. And the conversion is as follows. It might be clear at this point what the general rule is, but I'll just write it in completely clear terms. So, recall before we had the chain rule written like this. So f prime g of x times g prime of x. But we could rewrite this. We could say y equals f of w, and w equals g of x. And then we could write the chain rule as dy over dx equals, which is going to be this thing right here, this is dy over dx, equals dy over dw, which is this term right here, multiplied times dw over dx, which is this term here. So this is another way of writing the chain rule that seems prettier, and as I mentioned before, Leibniz was very big on choosing notation so that it looked appealing. Now, of course, one might say that it's too appealing and you could somehow get led astray, which the fact is, I mean, because it looks like fractions and it's not quite exactly fractions. Just remember it's not quite exactly fractions. That's not really going to be a huge problem until you get to multivariable calculus and everything sort of has to be reinterpreted. And that was discovered not long after Leibniz when multivariable calculus got going, which I think was, I don't remember when multivariable calculus initially got going, but it didn't take long. But yeah, so when you get to multivariable calculus, the idea of this being fractions will become insufficient, but for now, there's not really that much that can go wrong, except conceptually, of course, this is not the fraction of any usual sorts of quantities. So don't waste your time trying to figure out what quantities it's the fraction of, because of course it's the limit. we're working in limits in this class. So that is the chain rule, and we've gotten through more faster than I was initially thinking and expecting. There's a little bit more time, and maybe I'll do another example or two, but I would also, if we don't fully fill out the time, I would highly recommend rewatching this lecture, because we have really packed a lot into a short amount of time. So maybe I won't take up the full time, but in order to give you time to rewatch certain portions of this lecture. So let's do a couple more examples just to sort of drill matters. So say you have say you have sine of e to the x, and you take the derivative of this, it's going to equal dy over dw times dw over dy, times dw over dx, where y equals sine of w, and w equals e to the x. And so this is going to equal dy over dw is going to equal cosine of w, which is cosine of e to the x, so w is e to the x, and then multiplied times the derivative of w, which is going to be another e to the x. And so there we go, there's our answer, that's the derivative. Yeah. And so that's the chain rule, linear approximation, chain rule, implicit differentiation. That's a pretty loaded itinerary. So I'm not really going to go on to the stuff I planned for tomorrow. But I will give you a brief preview of what we're going to do tomorrow, so far, what we have been doing, and I'll draw this picture again tomorrow as well, but what we did today, and what we have been considering, is the tangent line to a graph. And if you think about it, this tangent line, it pulls away from the graph. In this picture, the graph is pulling down and the tangent line is just going straight. And so something we're going to talk about tomorrow is how to come up with an even better approximation that curves a little bit more along with the graph. But it still is completely computable, given pure information about this point, f of x, derivatives of f of x. So we have x0, f of x0, and just purely using derivative information at this point, we can better approximate this. We're going to be talking about how the tangent line moves over time. And so then another thing is going to be, when is the tangent line above the graph? When is the tangent line below the graph? What happens when it switches from being above to below or below to above? So that's the sort of geometric questions we're going to be considering tomorrow. But until then, have a good evening, and everything you need is attached.